In this section we're going to be learning about implicit differentiation. Well, we know what differentiation is, and we worked with differentiation in terms of the power rule, product rule, quotient rule, and chain rule, but we really haven't seen anything about this implicit business. So let's go ahead and first of all look at a function that we're kind of familiar with, y equal 1 over x. Well, let's look at another function that doesn't look as familiar, and that's xy equal 1. These are actually the same function. If you notice in this case, y is solved for in terms of x. This is called an explicit form. It's solved for explicitly in one variable. This form over here is called implicit because the x's and y's are mixed together, and I can't work through here and solve for only one value. Now I have to be kind of careful here because the word function does not always apply to all of these situations. Now in this case, if I had xy equal 1 and I divided both sides through by x, I get y equal 1 over x, and I get the same function back. So in this case, it doesn't matter whether I work with the explicit or implicit. Explicit is definitely preferred, by the way, but in some cases I will not be able to solve for x or y in terms of the other variable. So some implicit examples. And some of these, again, I can solve for, some of them I can't. So some implicit examples, xy equal 1. Well, I can solve for this one, y equal 1 over x. How about x to the 4th plus y cubed minus 8xy equals 7. I can't solve for x just in terms of y, and I can't solve for y just in terms of x, so this is definitely explicit. Another one might be something like xy cubed plus sine of xy to the 5th equals 7. Something like that. I cannot solve for x only in terms of y, and I cannot solve for y only in terms of x, so I'm kind of stuck here. Also notice you should always put parentheses around the arguments of your trig function to make it really obvious for what we're solving for here. So again, when I have these implicit forms, I can't always call them functions necessarily. And also how we take derivatives in Maple will change a little bit with an implicit form as well. So the first thing I'd like to do to get started is just to look at some examples and then to realize that we're going to be using the chain rule here. I think the easiest way to start with implicit differentiation is by looking at some examples. So again, differentiation means finding the slope of a tangent line. So let's go ahead and look at this example. Let's find the slope of the circle. Let's say it's the circle x squared plus y squared equals 25, and let's say at the point positive 3, positive 4. Now we can check this real quick. 3 squared plus 4 squared, 9 plus 16 is 25, so this point actually lies on the circle. Now I can't solve this just for x in terms of y or just for y in terms of x because of the squared. So we have to go through here and find dy dx. So we need to find the derivative with respect to x of the expression x squared plus y squared equals 25. Now one thing I know for sure, this is a circle with radius 5. Circle with radius 5 does not pass the vertical line test, so this is not a function. So x squared plus y squared equals 25. So I can think about this in terms of my derivative rules. So I take the derivative with respect to x of x squared plus the derivative with respect to x of y squared, this is going to be my chain rule, equals the derivative with respect to x of 25. So that's really what I'm up to here. Okay, well this first part's easy. The derivative with respect to x of x squared is 2x. The derivative with respect to x of y squared is the tough part. This is the chain rule. I bring the 2 down, decrease the exponent by 1, so this is an implied 1, and now I have to take it times the derivative within. My variable that I'm wanting to take the derivative with respect to does not match my variable, so I need to keep in mind I need to have the chain rule here. So I tack on a derivative of y with respect to x. And that's the implicit piece, and the derivative of a constant is 0. Now another way you'll sometimes see this written is 2x plus, and then sometimes instead of the dy dx you'll see a y prime. But this one kind of troubles me because a lot of times people multiply the y times y and get y squared, but remember this is a y prime It means the derivative of y. So I don't prefer this notation, but sometimes I do use it as well. Now I still don't know what dy dx is. So I have 2x plus 2y dy dx equals 0. So to solve, the first thing I'll do is subtract 2x from each side. Whatever you do to one side, you do to the other, of course. And then I'm left with 2y dy dx equals negative 2x. And then to finish solving, I divide both sides through by 2y. Whatever you do to one side, you do to the other. And what I get here then is dy dx. This implies that dy dx is equal to, the 2's cancel, minus x over y. That's the general slope of the tangent line, or the general slope of the curve at any point along the graph. Now I want to evaluate this at the ordered pair 3, 4. So I would get negative 3 over 4. That would be the slope of the curve at 3, 4. Well, let's go ahead and pull up Maple and see what Maple says about some of these things. Okay, in Maple we need to be careful about how we do things implicitly. First of all, let's input our function. It was x squared plus y squared equals 25. Semicolon ends the line. That's the function that we think that we're working with. So first of all, let's go ahead and look at graphing an implicit function. So if we right click on this and choose a plots command, and again you can write your own plot command, we want a 2D implicit plot. Now this is the deal over here. I have to choose between two things. The xy means the x is my horizontal and the y is my vertical. Yx means the y is my horizontal and the x is the vertical. And so that kind of defies our imaginations because we're used to the xy form. So choose the xy form. And in the case of a circle, it actually doesn't matter. So we won't see a big difference here, but choose the xy form. So if we plot that, we get our nice circle. Here's our x on the horizontal, here's our y on the vertical. So this is exactly what we think it should be. Okay, I'm going to come up here and I'm going to copy this and paste it down here. And I'm going to differentiate this. Now when we differentiate this, I right click on it and I choose differentiate, and now notice I have an option that's never come up before. Before it would just always come up with respect to, and I would choose x. But now I have this implicit portion because Maple recognizes that this is an implicit curve or an implicit graph. So let's choose explicit and let's see what happens here. This is the number of the derivative, first, second, third, fourth derivative. This is a bunch of stuff. You can just leave these checked if you want. It doesn't really matter. Here, though, we want to swap these out. Our dependent variable is our y. Our independent is our x. Okay, because I'm taking the derivative with respect to x, so that's our independent part here. So click OK, and you can see my derivative is negative x over y, just like I thought it was. Now, if we right-click on this, I should be able to evaluate these at our values for x and y. Now if I remember correctly, we used 3 for x and 4 for y. And we get negative 3/4 just like we did in our problem that we did out by hand. Now I could also find the equation of a tangent line. So let's go ahead and pop back to our lecture, and I'll copy and paste this into the lecture in a second. But for now, I want to find the equation of a tangent line at the point 3, 4. So I'm still working with the same exact graph, same exact function, but now I want to find the equation of the tangent line at 3, 4. And I already know my slope is negative 3/4. So we have y minus 4 equals negative 3/4 times x minus 3. Okay, so I have y equals negative 3/4 x plus 9/4 plus 4. So I distributed the negative 3/4 and I added the 4 across. Okay, so we have y equal negative 3/4 x plus 9/4 plus 4/4 is the same as 16/4, just to kind of make it easy on you. And I have y equal negative 3/4 x plus 25/4. That's kind of interesting, 25/4. So let's go ahead and pop back into Maple and graph this line and then plop it onto that circle and see what happens. Whoops. Here we are. So y equals, that was a negative, sorry, y equals negative 3/4 times x plus 25/4. Semicolon, that's what I think it is. I'm going to plot. This should be easy to plot. This is a line with a negative slope. Y-intercept at 25/4, which is 6 1/4, which looks pretty dang close. So I'm going to take this and I'm going to drag and drop it up here on the circle. See what happens here. And they kind of smushed our circle, so it looks a little oval right now, but just for scale you can see that, man, this is really nice. This shows exactly what I expected here. It shows this nice tangent at the point 1, 2, 3, up 4. So that looks great. So we actually have quite a bit to include in our screen snip here. Let's see if I can get it all. And again, I encourage you to graph things in Maple because it kind of gives you a nice picture of what's going on. And that's not going to include that very bottom of the circle, but that's okay. We know it's there and we'll include it. We'll sketch it back in. And again, because I'm changing the scale on this and mushing it around, that circle doesn't look quite as circular maybe as it could have. Then I'm also going to include the code that I used to find, I guess we don't need that part, the derivative and to evaluate it. But again, the thing to do is to input the function and then right click on it and see what happens. Another option is to go to the help function and type in the function that you're working with. You know, say something like implicit to get an idea of what you should put in to work with an implicit function. Okay, so those are our commands. So now here what we have is 1, 2, 3, up 4. This is that tangent line. Whoops. This is that tangent line at 3, 4, right there. And this is the equation of the line, y equal negative 3/4 x plus 25/4. So working with implicit differentiation has all the same rules as we've had before, but I need to remember that implicit part. Now the one we just did was actually fairly complicated, but I wanted to show you an example where it works just exactly like we would always think it would work in terms of finding equations of tangent lines, slopes of tangent lines, slopes of graphs. But it does work pretty straightforward. Let's go ahead and look at another one. Let's look at determining dy dx for the function, actually it's not even a function, y squared equals 3x squared plus cosine of xy. And again, the book doesn't always put parentheses around the arguments of your trig functions. Web work doesn't always do that, but I think it's a really super good idea to get used to putting parentheses around the arguments of your trig functions. It decreases the errors that people make when we're working with these. So to get started, the first thing I'm going to do is I'm going to go ahead and take the derivative with respect to x of every single term of the function. So derivative with respect to x. Derivative with respect to x. And I start differentiating. Now my variable of interest is x. That means anytime I take the derivative with respect to any other variable, I need to make sure I use the chain rule and tack on that dy dx. So the derivative of y squared, I bring the 2 down, decrease the exponent by 1, and now I multiply it by the derivative of y with respect to x, which is dy dx. Okay, now the derivative with respect to x of 3x squared is 6x. And then if you want to think about it, I'm actually using the chain rule here as well. The derivative of x with respect to x is just 1. So there is a dx divided by dx here. Now this is the interesting one. The derivative with respect to x of the cosine of xy is going to be a negative sine of xy times the derivative with respect to x of xy, where I'm going to have to use a product rule. So this was the derivative of the outside prime, and this is the derivative of the inside prime. So we have 2y dy dx equals 6x minus sine xy, and then I need to multiply this by a product rule. So to use the product rule here, I need those parentheses set up because it's this negative sine xy is going to have to distribute through. So I need a big set of brackets set up, and we work from here. Now the derivative of xy, so I'll have the first, times the derivative of x, the derivative of y with respect to x. So first times the derivative of the second, plus the second times the derivative of x with respect to x. Lots of algebra here. It's good stuff. So I have 2y dy dx equals 6x minus sine xy. Big brackets, x. The derivative of y with respect to x is just dy dx. The derivative of y is 1. The derivative of the inside is dy dx. Plus y. The derivative of x is 1. Now the whole thing here is I want to figure out what dy dx is, so I need to get all my dy dx's on one side, everything else on the other side, and kind of work from there. So I'm going to have to take this negative sine xy and distribute through. So I have 2y dy dx equals 6x minus, I'm going to pull this x dy dx out front, and the reason I want it out front is I don't want to mess it up with the argument of my trig function. And then I'm going to take this negative sine xy times y, which would be a negative y sine xy. Okay, still not done yet. I want to figure out what dy dx is. So basically I need to move this piece across where I add x dy dx sine of xy to both sides. Whatever you do to one side, you do to the other. We have to balance that equation. So over here on the left, I have everything together. I have 2y dy dx plus x sine xy, and I'm going to move this out to the end because I want the dy dx's on both of these to be on the left, or sorry, the right hand side of the terms. And then on the right hand side, I'm left with a 6x. This piece moved across, and actually it's summed to 0 here, minus y sine xy. Now over here, I want to factor out a dy dx. So there's a dy dx common to both of these, and if I factor it out, I'm left with 2y plus x sine xy. And over here, I have 6x minus y sine xy. And then, to finish this off, to solve for dy dx, I divide both sides through by the coefficient in front of dy dx. And again, whatever you do to one side, you have to do to the other. So these cancel, and I'm left with dy dx is equal to 6x minus y sine xy all over 2y plus x sine xy. There's my derivative. Now this is the general derivative. This is the slope of the line, or the slope of the curve at any point. So if I want to find the slope at a specific point, I don't need just x, but I need x and y. But this is my derivative, and you can see there's a ton of calculus in here and a lot of algebra as well, so you can't really give up on one of these because there's a lot of work to be done for them. Let's go ahead and look at another, and again we can't say function, so I'll say expression. And with this expression I want to look at a higher order derivative. Oh, wait a minute, I wanted to look at this graph in Maple first. So let's go ahead and open up Maple and look at the graph of this function in Maple. Woo, that was a long problem. Okay, so we want to look at the graph of y squared equals 3x squared plus cosine xy. So let's pop open Maple. So we want to look at the graph of y squared equals, so y squared equals 3x squared plus cosine xy. So that's the function I think I'm looking for, and let's have a look at the graph. Okay, let's go ahead and right click on this, and again you can write a plot command. I'm going to choose plot 2D implicit plot, and remember we have the example of xy or yx. I encourage you to do the xy, and here's my graph. Now this is kind of weird. It's definitely not a function. Let's go ahead and slap this into Maple and kind of get an idea of what we're looking at here. When we pop this into Maple, first of all, I'd like to plot a few points on here by myself just to see if this thing even makes sense, because that's kind of a weird graph. Maybe it's not going to let me. Oh, here it is, paste. And not only is it weird, but it's very big. Okay, so let's squish this down to size. So this is not a graph of my derivative, this is a graph of my actual function. So I want to look to see what's happening here at the origin. So this is at 0, 0. This is the point 0, 0. Notice it's not on my graph. But if I were to look at my function, y squared equal 3x squared plus cosine of xy, this would kind of give me an idea of what's happening here. So I would get 0 squared is equal to 3 times 0 squared plus cosine of 0, basically. So if I look at this, the cosine of 0 I know to be 1, so I'd get 0 does not equal 1, basically. So that's why it's not going through the origin. So this is just to verify it does not go through the origin. But let's see what is happening when x equals 0. Not the entire origin, but just x equals 0. For x equals 0, I get y squared equals 3 times 0 squared plus the cosine of 0 times y is 0. So I get y squared equals 1. Well, if I take the square root of both sides, I get y equal plus or minus 1, which is plus 1 minus 1. So this graph makes sense based on just a cursory look at the origin or near the origin here. So this is a graph of the original function, and what I just found was the derivative. And we can also look at this derivative implicitly in Maple as well. So to look at this in Maple, I have my original function. I right click on it, and again you can write a DIFF, a differential command, or a differentiate command if you want to. I'm going to right click, choose differentiate implicitly, and remember our independent variable is x, because that's what I'm taking the derivative with respect to. Click OK, and here's my derivative. And you know what? I'm not sure how that compares to what we found. Kind of looks kind of similar though. So let's go ahead and copy and paste it in to my document, and we can compare those. Maybe I can squeeze it in up here. Okay, so let's kind of compare here. So I have a minus 6x minus sine xy times y. So that looks good right here. 2y plus x sine xy, that looks good as well. There's a negative out front, and because if you distribute this negative out front through here, I will end up with a 6x minus, just like I do have in the numerator. So these are equivalent statements. So it's just cool to look at Maple and see what Maple has to say about it and to check your solutions with Maple. The last example we're going to do here is higher order derivatives, and these are really fun. I'm going to choose a fairly easy function, actually I can't say function, expression to work with here, so that way when we get to our higher order derivatives we won't have to focus so much on the differentiation as we will the substitution. So let's go ahead and look at the function 2x to the 4th minus 3y cubed equals 8. Now notice if I wanted to, I could probably go through here and solve for x. I could move everything on the other side and take the 4th root of each side. But remember, when you take a 4th root or any even root, you're going to end up with positive and negative values, so we kind of have to be careful here. What I would like to do here is to find, let's do y double prime. Find the second derivative. So let's go ahead and differentiate. Take the derivative of each term with respect to x. Okay, so this piece is easy. The derivative with respect to x of 2x to the 4th is 2 times 4 is 8x cubed. Now the derivative here would be 3 times 3 is 9y squared, but then remember I just took the derivative with respect to a variable other than x, so I need to tack on that dy dx, chain rule derivative of the inside, and on the right hand side the derivative of a constant is 0. Now I want to go through and solve for dy dx, so I get dy dx equals, I'm going to subtract the 8x cubed across and divide through by the minus 9y squared, and I get that dy dx is equal to 8x cubed over 9y squared. So that's not my final answer, it's an intermediate solution. Okay, now I want to find the second derivative? Well, one way to denote the second derivative is to take the derivative with respect to x of dy dx. And whatever you do to one side, you do to the other. So the derivative with respect to x of 8x cubed over 9y squared. So on the left-hand side, basically what I have here is d squared y dx squared. And this notation means second derivative. And then over here, to take the derivative of this, I need to use the quotient rule. So I have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I have 9y squared, quantity squared. And make sure the 9 and the y squared are both being squared here. Okay, now we haven't taken the derivative yet. So I have d squared y dx squared, and this notation just means second derivative, or y double prime if you'd like to think about it like that. Another way that we could look at this, and we actually haven't even taken the derivative yet, is y double prime, like I said. Now over here I have 9y squared. The derivative of 8x cubed is 24x squared, and I'm taking it with respect to x, so I'm good to go there, minus 8x cubed. Now the derivative of 9y squared is 18y, but I just took the derivative of y with respect to x, so I have to use that chain rule. And in my denominator I have this 9y squared quantity squared. I guess I could expand that or distribute the 2, 81y to the fourth. Well, there's my second derivative, but this is the cool part. This is what I like about the multiple derivatives. I know what dy dx is. Dy dx, if you look up further, is equal to this value, whoops, this value right here. So we can plug that in, and I end up with d squared y dx squared equals, looks like we have to grab a calculator here, 24 times 9 times x squared y squared. So we have 24 times 9 is equal to 216 x squared y squared minus, we have 18 times 8, 144 x cubed y. Now we tack on this dy dx. But dy dx was 8x cubed over 9y squared. And this is all over 81 y to the fourth. Okay, so we're going to keep chugging along here. Clearly layered fractions are not a good thing. We don't want to have these layered fractions. If I look at 9 and 144, 4 plus 4 is 8 plus 1 is 9. It looks like to me that because of the sum of the digits in 144 add up to 9, that 144 is divisible by 9. And I can also note that y cancels into y squared, so I can do some simplification here. I'm still going to have to go through and find a common denominator, which will be exciting. So I have 216 x squared y squared. Now what did we decide? 144 divided by 9 is 16. And this y cancels into one of the y squareds in the denominator. So it looks like I'm left with minus 16. Ooh, not just a 16, but a 16 times 8. I'll write that out so remember where it came from. X cubed times x cubed is x to the 6th. When you multiply like bases, you add the exponents. And what are we forgetting here? Oh, there's a y in the denominator. Now the y is only underneath this second term. It's not underneath this first term. This first term is technically only over 1. So here I have 81y to the fourth. So now I want to find a common denominator. The fun never ends on this one. So the common denominator is y. So I'll multiply top and bottom by y. So I have d squared y dx squared. So it looks like I have 216 x squared y cubed minus 16 times 8, which is 128 x to the 6th, and all of this is over y because I have that common denominator now. Now popping up here, 81y to the fourth is actually 81y to the fourth over 1, and when you divide by a fraction you're actually multiplying by the reciprocal. So when that reciprocates and pops up top, I get 1 over 81y to the 4th. Okay, still not done. This is fun. So d squared y dx squared. Looks like my numerator is going to stay the same. So I have 216. I might have a common factor there. We'll check it out in a minute. Minus 128x to the 6th all over 81 y to the 5th. There's my derivative. So first of all, there's nothing left to cancel here because there's not a y in both terms of the numerator, so I can't factor out a y. I could factor out an x and simplify this a little bit, and I will do that. 8, 9, 10, 11, nope. 81, 3s and 9s do not go into 128. They would go into 216, 6, 7, 8, 9, but it has to be a common factor to everything. So what I want to do is start pulling out things that are common, just to make it a little bit easier to work with. D squared y dx squared equals, okay, what is the greatest common factor here? So simplifying, I know we can pull out a 2 in the 216 and the 128. I know we can pull out a 4. Let's pull out an 8 and see if we can go any further once we get that out. I also note that there's an x cubed that's common. So if I factor out an 8x cubed, 216 divided by 8 is 27y cubed. 128 divided by 8 is 16x cubed all over 81y to the 5th. And then I notice here as well that 81 and 8 don't have any common factors, and I can't cancel or simplify any further. So there is my second derivative found implicitly of that original function. Now these can get a little bit long, and we have a ton of algebra to do here, but again, it's fun. It's good algebra, and you have to be careful you don't make mistakes. So the key here is to show all of your work. Don't skip any steps. Don't cancel without factoring, and don't make any of those common math mistakes, and you'll get correct solutions. And speaking of making mistakes, I think I found one. So let's go ahead and look back up here real quick. 216x squared y cubed, I rewrote this down here as a 3, so that messes that up. So let's fix that up. X squared y3 minus 128x to the 6th is still good. This still inverts and flips, but up here I can still pull out the 8, but I can't pull out an x cubed because I only have an x squared here. So the most I can pull out is an x squared. Okay, so if I pull out an 8x squared, 27y cubed minus 128, I need an x to the 6th, so this is going to have to be next to the 4th here. Problem at the very end. So this fixes up that derivative. Now let's go ahead and check what Maple has to say about this. Now in Maple, holy cow, what a mess. In Maple, what ends up happening is I have my function y squared equals 3x squared plus cosine xy. I believe that's what we were working with. No, we have a no trig function in this. 2x to the 4th minus 3y cubed equals 8. 2x to the 4th minus 3y cubed equals 8. So 2x to the 4th minus 3y cubed equals 8. Okay, so now if I want to differentiate this, so I go to differentiate implicitly, what ends up happening here, again I have to change my independent and dependent. If I take the derivative in 2 steps, take the derivative and then another derivative, I'm not going to get the correct solution. I need to tell it right away I want to find the second derivative implicitly. So let's go ahead and click OK, and there's my derivative. So again, let's go ahead and plop this into our notes so we remember how to do that. And that's the implicit plot. And the $2 means our second derivative. So let's right click paste. And let's see what our solution is. 8 over 81 x squared, 27y cubed minus 16. Yep, it worked. Good thing we made that change at the very end. And I'm also kind of interested to see what this plots as, just out of curiosity. So I'm going to copy and paste this. Semicolon, right click plots. Let's do 2D implicit. And again, we like the XY ordering. Did I copy the wrong one? Oh yeah, I did. We want the one without the trig functions. I was going to say that graph looks awfully familiar. Semicolon. Let's plot this now. Plot, 2D plot, XY. Kind of a weird graph, isn't it? kind of a parabola, but kind of not. So let's kind of paste this into our notes as well. Now this one looks like we could actually evaluate this almost as a function, except it looks like right around in here I could have a little bit of a problem passing the vertical line test, but I'd have to kind of zoom in on that to see if it actually is vertical or if it is actually just a very slight slant. So I'd have to look at that to see what's going on. So that's implicit differentiation. Remember, show all your steps. Don't make mistakes by copying down your numbers wrong or writing so you can't read your handwriting like I did. Make mistakes like that, we'll end up with wrong solutions, and if you have wrong solutions, of course all that work will be for naught.